All right, fasten your seatbelts, everybody, because today we're taking a deep dive into the world of models of computation.
Models of computation.
Yeah. Our listeners sent in some seriously fascinating stuff on it. Seems like they're looking for that, like, backstage pass to the core of computer science.
I like it.
Right. So we're talking about the kind of models that, they explain what computers can and can't do. Not like physical machines, but more like
The blueprints, you could say. We're going behind the scenes to see the blueprints of computation itself, those big ideas that shape everything in the digital world.
Exactly. And these aren't just theoretical what-ifs, living in some textbook.
Uh-huh.
What I'm getting from these sources is that these models have real-world clout.
Oh, absolutely.
They impact everything from, like, practical stuff like coding to, get this, the very limits of what we can even compute.
It's true. Think of them like different lenses we can use. Each one helps us understand something different about computers, what they can do, what they can't.
Oh, I like that, the lens analogy. So to kick things off, let's talk about, like, the big dogs, the classic models, right? The ones that built the foundation.
Got to start with the granddaddy of them all, right? The Turing Machine.
Ah, yes. The OG. This thing always blows my mind. So it was invented, like, way back in the 1930s, right? This theoretical machine.
1936, to be exact.
And it can simulate any algorithm. It's like the God mode cheat code of computer programs.
It really is. The Turing Machine is the big idea that there are, like, these universal rules to how computation works. Anything you can compute, no matter how crazy complex, it can be broken down into these simple steps that, in theory, a Turing machine could do. Makes you think, what's a computer really doing?
It's like this hidden code running under everything digital, right?
Yeah.
Okay, so we've got this super powerful but kind of theoretical machine. Then our sources mention the random access machine, or RAM, which feels a bit closer to, like, the computers I actually use.
Right. That's because the RAM model is kind of like looking at how modern computers access and process information, especially the whole memory thing, Okay. It gives us this framework to think about, like, okay, how efficient is this algorithm based on, like, how many steps it takes, how many times it's got to access memory, that kind of thing.
And this is where it gets really interesting, because these models aren't, like, perfectly identical to how things actually work, right? They make some assumptions. Like the RAM model, it assumes that you can access any memory location just as fast as any other, which, like, in the real world, totally not true.
Exactly. Think of it like using a map, right, to get around a city. The map shows you all the streets, the buildings, but it doesn't tell you about traffic jams or, like, construction.
Road closures, detours.
Yeah, exactly. These models, they simplify things, which is super useful, but we got to remember that, they're not the complete picture.
So it's like choosing the right tool from the toolbox.
100%.
Got to know the strengths and weaknesses of each model.
Just like a carpenter wouldn't, use a hammer for every single thing.
Please.
Computer scientists have their own set of tools.
Love it. Which leads us to some of the, let's just say, more out there models. Get ready, because in Act 2, things are about to get weird.
Weird is my middle name. All right, so you ready for this? Combinatory logic.
Hit me.
Okay, so imagine, like, building everything you need with only functions. It's like, a Lego set, but there's only one type of brick.
Okay.
No variables, no data structures, just pure, beautiful function logic. Combining, transforming, the drill.
Okay, I might need a few more bricks in my Lego set to really grasp this one. Like, functions combining to create other functions.
Yeah. It's pretty wild, I'll admit. Let's say you have this simple function, right? Just adds 2 numbers. That's it.
Okay, got it.
Combinatory logic says you could use that one function just by cleverly combining and transforming it to make a whole other function that, like, multiplies numbers. It's like super minimalist computation.
So it's like composing a whole symphony of computation, but with just one instrument.
I kind of see it, but I'm also kind of glad our computers use more than just one function. Speaking of which, our sources mention finite state machines, which seem a bit more, down to earth.
Totally.
They're like the reliable workhorses of the model world, right?
Absolutely. And you see them everywhere, even if you don't realize it. Think about your microwave.
Okay.
It's got those few settings, right?
Yeah.
Heating, defrosting, off.
Right.
And it switches between them based on what buttons you hit.
Right.
Bam. That's a finite state machine.
Ah, now I get it. So from minimalist functions to the brains of my microwave, we've covered some ground. But then, oh boy, then things get even weirder with cellular automata.
Oh, yeah, cellular
Our
automata.
listener described them like grids, and each cell's like, what am I going to do? And it's all based on what its neighbors are doing. It's like a computer simulation of life itself or something.
It really is. There's this famous one, Conway's Game of Life. You start with this grid of cells. Some are alive, some are dead. I've seen those. They're so cool.
Right, and you apply these super simple rules, like if a cell's got too many neighbors, it dies, that kind of thing.
Yeah.
And then, boom, you get these crazy patterns evolving, growing, changing.
Yeah.
Like watching a digital ecosystem, right?
So mesmerizing. But, like, practically speaking, what are they used for?
Oh, all sorts of stuff. Traffic flow, forest fires, even how diseases spread, complex systems. By simulating how they behave at, like, the smallest level, we can kind of get a handle on and see how they might change in the future.
Whoa, it's like a digital crystal ball.
Exactly.
Okay, that is cool. So we've got all these awesome tools to understand computation, from Turing machines all the way to these cellular automata. But plot twist, Act 3 is where our sources are like, hold on, even these models have limits, especially now with all this crazy modern tech.
Totally. Things are changing fast.
Right. We've got these multi-core processors that can do a million things at once.
Yeah.
And then there's quantum computing, which feels like it's straight up bending the laws of physics.
Yeah.
Are you saying our crusty models might not cut it anymore? It's like we've finally figured out how to map the stars, and then, bam, someone invents warp drive.
Yeah. Our models are great at explaining how computers work, right up until they don't. Parallel processing is a great example. Our old models, they think one step at a time.
Right, nice and sequential.
Exactly. But now we've got these processors with multiple cores doing all this stuff simultaneously. It's like trying to understand a whole symphony by listening to each instrument play their parts separately.
You lose the orchestra, the way it all comes together.
Right. So how do you even begin to model that? How do you model what happens when things aren't just happening one after another?
Yeah, that's got to be a brain twister.
Yeah, it is. It is. But computer scientists, they're clever, right? They're developing new models all the time. These new models, they're focused on concurrency, how processes talk to each other, how to keep everything in sync when you've got all this stuff going on at once. It's a wild ride.
And then there's quantum computing, which feels like it's not even playing the same sport, honestly.
Oh, absolutely. Quantum computing is like, okay, you know how our current computers use bits, right? 0 or 1.
Right, the building blocks of, well, everything digital.
Yep. Quantum computing uses qubits. And a qubit, well, it can be 0, 1, or both at the same time.
At the same time. Now, how is that even possible?
It's quantum mechanics. It's kind of like, imagine flipping a coin and it lands on heads and tails at the same time.
Okay, now my brain's officially broken.
It's one of those things that just, it kind of breaks your brain a little bit until you sort of accept that that's just how it is at the quantum level.
So, okay, let's say I can accept that. It's mind-blowing as it is. How do you go from a qubit being in 2 states at once to, like, actually computing something?
It's all about how these qubits interact. They can do things that regular bits just can't. Like, they can link up in this crazy way called entanglement. Imagine 2 coins flipping and landing on the same side every single time, no matter how far apart they are.
That's wild.
It is. And because of that, quantum computers can explore tons of possibilities all at the same time. They can tackle problems that would take a regular computer, like, millions of years, and solve them in a fraction of the time.
So we're not just talking about faster computers.
Yeah.
We're talking about a whole new way of thinking about computation.
Exactly. It could revolutionize, well, pretty much everything. Medicine, materials, how we keep things secure online, artificial intelligence.
It's like opening a door to a whole new universe.
It really is.
Okay, so for our listener out there who is probably feeling as mind-blown as I am, let's bring it back down to earth for a second. Why does all this matter if you're not, like, planning to build a quantum computer in your basement anytime soon?
Because these models, they're more than just, like, theoretical toys. They reflect how we understand what computers can do, and as we've seen, that understanding is always changing.
It's like the better our maps are, the more places we can explore.
Exactly. And the more we understand these models, the better we can design algorithms, write code, build technology that pushes the boundaries of what's possible.
So even if we don't get all the nitty-gritty details, just knowing these models exist, it's like it opens our minds to what the future could hold.
Right. It sparks that curiosity. And Who knows, maybe our listener will be the one to make the next big breakthrough in computation.
Now, that would be amazing. Well, this deep dive has definitely left me with a lot to think about in the best way possible. It's like we took a journey to the edge of what's possible and got a glimpse of what might be out there.
That's what we're here for.
A huge thank you to our listener for sending in this amazing topic. We hope this deep dive has left you feeling inspired and maybe just a little bit mind blown. And as always, keep those minds curious.